In this question, we're going to design a max stack. You're supposed to design a custom data structure that supports both stack functionality as well as priority queue functionality. So stack functionality allows you to push an item into your data structure. When you want to retrieve the item should be the last item that you just push it in. We will talk about time complexity later. For the priority queue functionality, you can also push item in, but whatever item that you retrieve, this item must be the maximum element inside your data structure. So we should support two operations. Top, that means the latest element that is pushed in, as well as peak maximum, which is to retrieve the maximum element inside our data structure. Of course, we can also choose to pop the latest item as well as pop the maximum item. Now, the fact that this is an interview question means there is requirement on time complexity. The time complexity should be the read time should be all of 1. That would mean that the write time would be more than all of 1. The write operation will include push, pop, and pop max. So these three we can tolerate more than all of 1, but as for top as well as peak max, these are read operations, they must be all of 1 constant time. Suppose this is the series of instructions that you want to have. First, we push the number 3 into our data structure, and I'm going to use stack as well as priority queue to simulate our data structure. So when you push 3, we add 3 into our stack. We also add 3 into the priority queue. When you push 4, we add 4, push 4 into the priority queue. When you push 3, we need to do some editing and push 3 here, 4 there. You push 2 again, we do some more editing. So you get 2, 3, 3, 4. When you push 1, we do some more editing. 1, 2, 3, 3, 4. For priority queue or max heap data structure, I'm using this shape just for simplicity's sake. The actual data structure is a tree. The actual data structure is an array with tree-like visualization. So the total time complexity to form a priority queue is linear. Now, if you want to read the top of our data structure, we should read the top from stack, so it should be 1. If you want to peek the maximum, it should be 4. You should peek from our priority queue. So what happens if you want to pop an item? Now here comes the issue. When you want to pop an item, you should pop from the top of our stack, so 1 should be gone. But you should also do some editing inside our priority queue. But it's not obvious where 1 is inside our priority queue. So you may end up doing even linear work. You may have to remove everything out of our priority queue, 4, 3, 3, 2, and put them into a temporary storage. Then once you see the 1, you remove this 1, then put all these items back in your priority queue. And that is very expensive. So here you see our problem is not trivial. It's not trivial at all. As a matter of fact, I would argue that this is a medium level difficulty question. But if you have done LRU cache before, this question may be easier for you. So let's continue. So we pop 1 is gone. Let's also do the editing out of the priority queue. So you will have 2, 3, 3, 4. And we want to pop the max. So we pop max, we should pop from the priority queue, so 4 is gone. But you should also edit the stack. But it's not obvious where 4 is inside our stack. We know 4 is on top of our priority queue, but we don't know where 4 is inside our stack. So you have to do the similar thing, have a temporary storage, pop every item and store it into a temporary storage. Once you find 4, you pop 4 out, then you put the item back in. So this is also a very expensive operation. Again, pop as well as pop max are not trivial. So we know we need to be creative in our solution. And when you need to be creative, some data structures should come to mind, like hash table as well as doubly linked list. And indeed, the solution is hash table and doubly linked list. And if you want to have some intuition around it, you can think of pop max operation. If you want to remove 4, we also need to remove the corresponding node inside our stack, right, which is 4. And in order to have a very cheap access into this node, right, so this is where you may think, oh, maybe I need a hash table, so I can access the element inside your stack straight away and remove it. And of course, you're not allowed to remove an item in the middle of a stack. So what other data structure are you allowed to remove an element in the middle very cheaply? That will be a doubly linked list, right? If you have a doubly linked list and I want to remove an item in the middle, all I need to do is to update the pointer, right? So this is gone. And this is a constant time operation. So this is the intuition for a hash table and a doubly linked list. And of course, we also have to have max heap functionality. So you need to have hash table. You need to have doubly linked list. You also have to have a max heap. Now in C++, we can use 2 data structures, a list as well as a map, which map an integer into an array of linked list node. So vector is dynamic size array and linked list node. So your integer is the key. The value of the hash table is an array of linked list nodes. By the way, a list in C++ is a doubly linked list. This may be confusing. It will make more sense when we come to the actual code. So we are going to use a doubly linked list to simulate a stack and use our hash map with ordered keys to simulate our max heap. Let's walk through the example. When we push 3, we just push 3 into our doubly linked list. Hash map will have a key and a value, and key is just the value, and value is the node. So value is this node. As a matter of fact, the value is an array of node. So let's just put array symbol. And you are putting the actual node or the reference of this node inside your hash table. That's where you get your constant time access. Let's keep going. You want to push 4. Okay, let me just remove this arrow. But you should know that inside my hash table, we store nodes. From that node, you have access to your doubly linked list node. Okay, so when you push 4, you should also push 4 into our hash table. And our hash table will always have ordered keys. By the way, that is the map data structure in C++. If you want unordered keys, you will have unordered map. And we are using map here. So keys will be sorted at all time. So when you push 4, 4 will have the node 4. So this 4 is pointing to that linked list node. So let's keep going. When you push 3, you push 3 into a doubly linked list. Then you also push 3 into the hash map. And these 2 nodes are distinct from each other, right? This is a node, this is a node, and they are distinct. So in your hash table, your first node is pointing to this node, your second node is pointing to this node. Let's keep going. When we push 2, so you add 2. Now because you push 2, we should adjust our hash table a little bit. So let me clean up the space. I have just rearranged our hash table because the keys are always ordered. Now the 2 will have the node pointing to here, 3 is pointing to this 3 is pointing to this 4 is pointing to this. Okay, last we push 1 in our hash table and map to 1, so this one will point to this one. Okay, now let's see what happens when we want to pop. When we pop, we will pop at the end of our doubly linked list. And we know the value is 1. And to get the end of a doubly linked list, the time complexity is constant. So you can just remove this guy. You should also update the hash table. So you just find out the corresponding value of 1. And there's only one element, so you remove it. And because now our array is empty, this array is empty, so our key is no longer valid, we should remove this entry completely. So 1 is gone. Let's now do pop max. When we do pop max, we should no longer pop from here, right? Because we should pop max. What is the max? We can access the last key in our hash table, which is this. This is also a constant time operation. So we should pop, well, there could be multiple nodes. In our case, there's only one 4. So 4 is pointing to this guy. So let's pop 4 and remove the entry. Now let's pop 4 from our linked list. So you redraw the link. This is gone. This operation is still constant. Okay, so let's continue popping max. When we want to pop max, we would need to go to the end of the hash table keys, which is 3. 3 will map to an array of linked list nodes. So we have 2 here. And we know the back is the later one to come in, right? So this is a later one, so we should remove this. And this is pointing to this 3, right? The front 3 is pointing to this 3. We don't remove that. We should only remove this one. So we first pop from our hash table array. So this 3 is gone because there are still elements inside the array. So we do not remove the entry. Then let's remove the node from our doubly linked list. So we redraw the link. Now this 3 is gone. I hope this gives you an intuition of the relationship between our hash table and our doubly linked list. Our hash table is storing an array of linked list nodes, well, of the references of the linked list node. And when you want to remove a linked list node from a doubly linked list, it is constant time. Now let us write the actual code. Let us first initialize the data structure. First data structure is our doubly linked list. Let us call it DL. The second data structure is our ordered map. So the key is just an integer. The value is a array with the linked list node. So we're gonna put iterator. Let's just call it M. I think I need one more curly brace. When we initialize, let's just clear it. M not clear. Okay, I'm not sure whether I'm gonna have syntax error, so I'm just gonna test for syntax error. No error. Okay. So when we push, we are just gonna push the value into our doubly linked list because our doubly linked list is simulating stack. When we push to the hash table, now mx is an array, so you can do array pushback. The reference to the last element of our doubly linked list. So you can do minus minus and DL. Let's do the easier ones first. So top is easy. Top is the last element of our linked list. So that will be reverse begin, DL, and dereference. Peak max, that will be the last key of our map. So you can do reverse begin, map, first. Let's check for error. No syntax error. Okay. Now let us do pop. So the item that we want to pop is going to be the last element of our doubly linked list. So that will be reverse begin, DL, and dereference it. So we will return it. Of course, before that, let us pop from the doubly linked list. We also should pop from the hash table. So hash table m return. We want to, because this is an array, we want to pop the last element. We are also guaranteed that the last 4 operations won't be called when stack is empty. So we are guaranteed that all the operations are valid operations. These are the last 4. They are always valid. Now, if it is empty, we should remove from the hash table entry. So m.erase red. Actually, we can reuse top, so I'm just gonna put this as top. And for pop max, we can put the max as peak max. Return, and we can get a reference of the actual linked list node, which will be the last element of that array. Now we can erase this node from the linked list. This is constant time. So now we should also pop from the hash table. And let's do a check. Reuse the code. And let's see if this works. Let's see if it works. Oh my god. Okay, let's submit. So there we go.